So the first thing about graphs, basic curves. Right? If we know what a basic curve looks like, it's really easy then to work out domain and range and all those sorts of things. If we know what the picture looks like, we can solve a lot of those problems. So the basic curves, these are the things we should know. Straight lines, of course. Y equals x being the most basic, I guess, of all the straight lines. And in order to recognise it, we go, oh, look at that. Both of the pronumerals are to the power of 1. That must be a linear function. Okay, then we moved on to parabolas. The most basic one, y equals x squared. So one pronumeral is power of 1 and the other the power of 2. Now, why are these two functions so important? Well, that's what we learn in polynomials, that everything can be factorised down to be a combination of linear functions and quadratic functions. And that's why we spend so much time investigating those two functions, how we find solutions and things like that, because everything can be broken down to a combination of linear and quadratic functions. The general parabola, of course, ax squared plus bx plus c. Cubics, oh, now the power goes to 3. Woohoo! So one of them is power 3, one of them is power 1. So then we went to polynomials in general. We did a lot of work on those. Hyperbolas. Now, the very first one we saw, y equals 1 on x, was our standard one, and we thought, oh yeah, that's a hyperbola. But of course, in extension 2, we then saw, oh, actually there are other ones they can look like, and there's x squared minus y squared and things like that. Basically, those ones, the basic ones, y equals 1 on x, if you see a pronumeral in the bottom of the fraction, you've probably got some sort of hyperbolic function. Or if you see two pronumerals multiplied together, that could be a clue that it's going to be hyperbolic. The exponentials, y equals a to the power of x. The clue is, hey, look, there's a pronumeral in the power. Could be an exponential. Circles, x squared plus y squared is the radius squared. So the coefficients of the x squared and the y squared are the same. That's how we recognise that one. Oh, and to the power of 2, of course. And then ellipses was when we changed the coefficients. Still the same sign, mind you. And then, as I say, if the signs were different, then we're back to that other type of hyperbola that we investigated. Logarithmic functions, the giveaway there is you see the word log. That could be a log function. Trig functions, sine, cos, tan. Now, the interesting thing about log functions and trig functions, and for that matter, inverse trig functions, those of you who end up doing any mathematics at a university level will find that all of these can be approximated using polynomials. And again, this is why polynomials are so important. And then every polynomial can be written as a combination of linear and quadratics, and why they became such important functions. As I say, these are the things we've been throwing at you down your throat, shoving all these ideas down your throat, all through junior school, and you just thought, oh yeah, well, that's nice. Parabola, oh yeah, beauty, what's the point? But now we're at a point where we can sort of put this all together and go, hey, this is why it's so important. Okay, odd and even functions was an interesting idea because that then told us about symmetry. If we want to know symmetry of the shape. So remember, odd function negative x, negative function x, and that's the one with rotational symmetry. Even function negative x is function x, that one has an axis of symmetry. So symmetric about the y-axis. Symmetry in the line y equals x. We haven't talked a lot about it. We talked a bit about it when we looked at inverse functions, you might remember, and we said they were symmetric in y equals x. Basically, if you look at a function and you can swap the x and y around and it doesn't change the function, then that must be symmetric in y equals x, because basically what we're saying is it is its own inverse. Because we're going to find inverse functions, we said swap the x and y around and see what the new function is. So if it doesn't change the function, it is its own inverse, therefore the shape is reflected in the line y equals x. So x cubed plus y cubed equals 1. If I swap the x and the y around, I'm going to get the same thing. Y cubed plus x cubed is 1. So I know this thing is symmetric around y equals x. All right, this idea of dominance. Now this is useful to see the limits out at infinity, or what's happening out at infinity or negative infinity. as x gets large, so as I say, out to infinity, does a particular term dominate? Polynomials. In a polynomial, the leading term will always dominate. That's why back when we started looking at sketching polynomials, one of the things I said, oh, where does it start and finish? Oh, it'll do the same as what the leading term does. It'll start, so you just looked at the leading term and say, oh, no, it starts up here, finishes down here. What I was actually doing was using this idea of dominance. So out of those extremities, as x was really big, it'll act just like the leading term. So in that one, x to the power of 4. Now x to the power of 4, I know, starts up at the top, finishes up at the top. So this particular function would do that as well. Okay. Exponentials. E to the power of x is going to win it every time. Because exponentials get quick, get steep really, really quick because of the powering, because you like double, then double again, and double again, and double again. That's if it was 2 to the power of x. So e to the power of x, it would get steeper even more. So that's what they say. In general, look for the term that will get the steepest the quickest. And that's the term that's going to dominate. The one that gets steepest the quickest. Now, of course, if you're ever unsure, sub in big numbers. And then so you might start with, 100. Okay, now I'll sub in 1,000. Now I'll sub in, and you'll get an idea of what's happening as x is getting bigger and bigger and bigger. Is it also getting bigger? Is it approaching a particular number? And so on. Asymptotes. Okay, we know about our vertical asymptotes. Bottom of the fraction can't equal 0 was the most basic idea for that. Horizontal and oblique asymptotes. Top of a fraction is a constant, then that fraction can't equal 0. That's when we were talking those polynomial type functions. So if we did a polynomial division, the quotient would turn out to be the asymptote. So if the order of the numerator is greater than or equal to the denominator, do your polynomial division. Now remember, it is okay for curves to cut horizontal and oblique asymptotes, because again, that's just telling you what happens out of the extremities. So out at infinity and minus infinity. The vertical ones we can't cut. Vertical ones we can't cut. Oh, our very special limit. Now, it was actually a 2-unit idea. Not the 2-unit use it that much. You do see it in 3-unit. And that's this one, that special limit. The sin x on x one. If you got some harder graphs, it might help. Right? So remember that idea. Because if you're drawing a graph of, well, let's say sin x on x, you know it's approaching 1 at 0. Won't actually equal it though, so you have a point discontinuity there. All right, but then, of course, we discovered this whole idea of calculus to help us draw curves. Okay. So it's still a terrific tool. Critical points, stationary points, inflections. If you need to find those sort of points, the calculus will help you out. So critical points. Okay. If the derivative is undefined, it usually means we have a vertical tangent at that point, because what we're saying is the slope is infinite, so we must have a vertical tangent. So they are what we call critical points. Now, technically, stationary points are also critical points, but they have their own special name. So when we talk about a critical point, I'm sort of talking about the one that doesn't have another special name. So that's the ones with vertical tangents. Because stationary points, as we know, that's when the derivative is equal to 0. We have a horizontal tangent. Maximum, minimum turning points. They were really important when we were solving the problems, when we were using the graph to find what is the maximum area, the minimum area, things like that. So we wanted to know how high up it goes. We wanted to find those turning points. It had to be a stationary point, and then depending on its concavity. If it was concave up, happy curve, here I am, down the bottom. So it must be a minimum turning point. If it's concave down, sad curve. So maximum turning point. Sometimes if the function is difficult to differentiate, then don't bother finding the second derivative. Just have a look at what the first derivative is doing. Because if it's going positive, naught, negative, must be a maximum turning point, and vice versa. So sometimes that's quicker than finding the second derivative on some of those more complicated functions. So our inflection points. Now it's when the second, sort of like we go up a level. That was first derivative equals 0. Now we've got second derivative equals 0. It has no concavity at that particular point. Most textbooks, of course, then say, like I just did here in the last one, test either side, which is a terrific way of doing it. Again, if it is a complicated function, have a look at what the second derivative is doing to see if it's changing concavity. But of course, you could use the third derivative idea. If the third derivative does not equal 0, what it's saying is then there is a change in concavity, because the third derivative must measure the change in the second derivative. Second derivative measures concavity. So if it has a value, then there must be a change in concavity. Okay? The actual rule is, it's not so much the third derivative, it's if the first derivative that does not equal 0 is an odd one, third derivative, fifth derivative, seventh derivative, ninth derivative. Goodness me, if we had to differentiate that many times, let's just test either side of the point. That's going to be a lot quicker. But the actual theory is, if you keep down, and if it turns out to be the first time, when you sub that point in, you don't get an answer of 0. If it's an odd one, then that's an inflection point. If it's an even one, then it would be a turning point. So that's the actual full theory. Very rare we get ones where it's not the third derivative, and we could just use that. As I say, testing either side certainly is a lot quicker if we have to go further than the third derivative. Now we have these special inflection points. So it's an inflection point that is also a stationary point, just like our basic cubic over there at 0, 0, horizontal point of inflection. Horizontal point of inflection. Increasing or decreasing. And people sometimes forget this. And the words sort of explain, because they say, hey, when is this function increasing? And simply saying, well, when is it going up? Well, if it's going up, if you were to draw a tangent to the curve, then it must have a positive slope. And so all we need to work out is when is the derivative greater than 0? If the derivative is greater than 0, the curve must be going up, because we've just drawn a tangent with a positive slope. So that's when it is increasing in value. And if the first derivative is less than 0, that must be when it's decreasing in value. A good old implicit differentiation. This helps with relations rather than functions. Because most of the time we're dealing with functions and we have it as y equals, we can differentiate. Fantastic. You get things like the ellipse and the hyperbola, which are relations rather than functions. Then implicit differentiation allows us to do that. Because basically, and we'll do it on x cubed plus, we'll go back to that one. But the reason why is, if it's a function, when I differentiate it, I'll just have to substitute in the x value. And that's fine, because it's a function, for every x value there's only one possible y value. In implicit differentiation, you remember, we end up having to substitute in an x and a y value. Because have a look at the circle. If I was just to substitute in the x value, there's two possible points that I'm talking about. And so that's why I also end up having to substitute in a y value as well, so I can isolate, hey, which particular point are we talking about to find the slope? So let's look at x cubed plus y cubed is equal to 1. So things I note, as I mentioned before, it's got symmetry in y equals x. There's y equals x. It's symmetric about that. Okay. X-intercepts and y-intercepts are quite easy to find. 1, 0, and 0, 1. Okay. There's 0, 1. There's 1, 0. All right. Oh, now this one you might not have picked straight away. This is going to be asymptotic to the line y equals negative x. And here's why. You see, y cubed would equal 1 minus x cubed. So if it's always 1 minus x cubed, then it can't equal minus x cubed. Now, if y can't equal minus x cubed, y can't equal minus x, that's going to be an asymptote. So, not easily picked up, but there you go. So there we go. There's y equals minus x. That will turn out to be an asymptote. Differentiate implicitly. There's my derivative, minus x squared on y squared. That's always going to be negative. So I've got x squared on y squared. So I know this curve is always decreasing. It's always going down. Okay. What else do I know? At 1, 0, and 0, 1, I've got my critical points and stationary points. Because at 1, 0, I'm subbing 0 in for the y value. 0 on the bottom of the fraction, so I've got a vertical tangent. 0, 1, I'm substituting in 0 for the x value, I've got a horizontal tangent. All right, here we go. Whee! There it is. That horizontal and vertical tangent, if you think about it, because it's symmetric, that makes sense. Because if at this one it's horizontal, then when I reflect it, that one's got to be vertical. So there's x cubed plus y cubed equals 1.